All right, so we're back with another lesson. Move this down there. So this lesson is lesson number 5 for Unit 1 Kinematics on motion graphs. This lesson is pretty much going to be a review of grade 11 because we did a lot of motion graphs in grade 11, but motion graphs are very important in understanding motion. All right, so we have 3 types of motion graphs that we analyze. We have DT graphs, and that D stands for position. It doesn't stand for distance, it doesn't stand for displacement, it stands for position. So these are position time graphs. Okay, on the graph we're looking at the computer, it says distance from starting line. Now, even though they're using the word distance, it's distance from a certain origin. And so therefore that's the definition of position, right? Where you are from a certain frame of reference, from a certain point of origin for a certain coordinate system. Then we also have VT graphs, which are velocity time graphs, and AT graphs, which are acceleration time graphs. And we analyzed all of them in grade 11. And specifically what we also did is how to go from one to another. So here we have a distance time graph. We have a large slope, a smaller slope, and then a slope of 0. And if we're to watch what happens, large slope we're moving fast, and then slower, and then we stop. So the slope of our position time graph, tells us the velocity. Now if we switch this to a velocity time graph, it just looks like this. Right? They're horizontal lines. Now horizontal line on a DT graph means your position isn't changing. On a VT graph it means your velocity is not changing. If you had changing velocity, which I can't do on this simulation, but if you had changing velocity, then the slope of that graph would give you acceleration. Similarly, if we were to look at the area under a graph, so let me just change this to make the number nicer. Oh, it won't let me. Oh, I can change it up. Okay, so let's look at this. So in about 1.3 seconds, we're moving with a velocity of 30. Okay, so if you did find the area under that, 30 times 1.3, I'm assuming it's 1.33333. 30 times 1.333, so width times height, gives us 40. And that tells you your displacement. It tells you what your change in position was. Okay, from 0 to 4. It's very important that it tells you your change in position, because I can do something like this. Okay, and so what about from here to here? Okay, well, what displacement is going on there? Well, if we look over here, if we were to find the area under this portion right here, which is around, no, what would this be? It's 1.3 seconds to 2.7 seconds. So maybe around 1.4 seconds is the width, and the height looks to be just under 10. Okay, so 1.4 times, I don't know, 8. Okay, and it'll give you about 10. Well, that 10 is obviously not equal to 30 here, is it? However, it is equal to the change in position from here to here, from 20 to 30. Okay, so very important. If we find the area under a VT graph, it doesn't tell you your position, but it tells you your change in position. Similarly, if we were to find the area under an acceleration time graph, we would find the change in our velocity, which makes sense in a way, because acceleration is change in velocity over time. So if you take this equation and multiply both sides by time, right, on your graph, right, this would be height and that's width. And when you multiply them, you don't get velocity, you get change in velocity. Right? Similarly, displacement, not position, displacement is equal to velocity times time. So if you were to rearrange this and solve for, actually no, we don't need to rearrange that at all. Right, there's your height of your VT graph, and there's your width of your VT graph. So when you find the area under that graph, you get displacement, not position. So that's how you go back and forth between the graphs there. Now let's look more at examples of curved graphs. Okay, if you have a DT graph, okay, now of course this is obviously something that's not moving. This is something that's moving with a constant velocity. But what about if we have curved graphs, like that? What's happening there? Well, something's position is obviously changing. So they're moving, but are they increasing their speed, decreasing their speed, or moving at a constant velocity? So to check this, well, you can use a ruler. Okay? So right here, at this point, okay, let's take this point right here. Let's take a couple points. This one, this one, this one, and this one. So if we analyze these points, and to find the instantaneous velocity at one of those points, you need to find the slope of the tangent at that point. Now, without calculus, all we can really do is sort of estimate the tangent with a ruler like that. And why am I out of focus? There we go. Okay. And so here you have a slope that's not too steep. And then over here, it's steeper, and then steeper, and then steeper. So what's happening is our slope is increasing, meaning our velocity is increasing. Okay. And if we were to take all of those slopes and plot a VT graph, you would get something like this. And then if you were to take that slope and plot an AT graph, you would get something like that. So this is your VT graph, and that's your AT graph. Well, that would be AT and VT. Okay. Now, if you look at it, there kind of is a relationship here. This is a horizontal line. So if you were to write an equation for that line, you would just have it equal to some value, some constant. This is a linear one. So if you write an equation for this line, you would have it equaling, well, a linear equation, right? Some variable to the exponent of 1. And here, it looks like a quadratic, and in fact it is. It would be a variable to the power of 2. So this is to the power of 0. This is to the power of 1. This is to the power of 2. You might be asking, can you have a DT graph which is cubic? Of course you can. Right? You can have something that's even steeper and have it say something on the order of x cubed. In that case, your VT graph would be something on the order of x squared, and your AT graph would be something linear on the order of x. However, we're not going to analyze those situations. This is actually called a jerk. That is the technical term. I'm not just being rude. Right? The technical term for a change in acceleration is called a jerk. Right? But we are not going to analyze those. We're going to stay in just quadratics, okay, for DT graphs, and just linears for VT graphs, and just constants for AT graphs. All right, so on the front page, I do have some different curves, which you should know. We went over the first one, right? It's sort of an upward curve. Your slope is increasing in the positive direction, therefore you're speeding up. Okay, so there's lots of ways. These are all analyzing whether or not you're speeding up or slowing down. The next one is kind of like that. Now in this case, if you analyze the tangents at points, you'll see that the tangent is actually getting smaller and smaller and smaller. Okay, so in this case, you're actually slowing down. But what about a case like you slowing up or are you speeding? Oh, sorry, are you slowing up? Are you speeding up or are you slowing down? In this case, if you analyze the slope is increasing, but it's increasing negatively. Remember, all of these are just vectors. Okay, so increasing negatively is still increasing, it's just increasing in the opposite direction that you chose to be the positive direction. So if you chose forward to be positive, this just means you're increasing negatively. Okay, so if this is our dt graph, well, I would say you're speeding up going backwards. Okay. However, if I were to write it like this, okay, in this case, you're still going backwards, but in this case, you're slowing down. And if I were to do something like this, okay, in this case, initially, you're still going in the forward direction, but you're slowing down, then you stop at some point, and then you're speeding up. Okay, but you're speeding up in the opposite direction. So that means you're traveling now in the opposite direction. You're still on your dt graph, you're still in the positive area. So wherever you chose to be the origin, let's say this marker is going to move and my hand is the origin. I can just throw it up and that perfectly represents this graph. Okay, here it's moving away from the origin, but its speed is decreasing. It comes to rest at the top, and then its speed increases until it reaches the origin again. If I didn't catch it and it just continued to fall, well then we would just do this. Have it cross the origin and keep going. So that kind of looks like a projectile motion question, and it does. So the dt graph for a projectile looks exactly what it should look like, a parabola. But for now, let's analyze this question on the back. So we're going to examine this graph. It is a VT graph. Let me try and draw this here. This. My drawing is terrible, but you have it on paper, so you see where I'm going here. So it's 1 second, 2, 3, 4, 5, 6, and 7. Okay, and it says, how far did the jogger travel in the first 4 hours? Now, just how far, it just wants to know distance. So the units here, it's actually kilometers per hour south. So here's our velocity in kilometers per hour south. So our positive direction is south. That means initially we're moving north. Now to figure out how far you've gone, well, we need to find the areas. Let's call this A1, A2. This will be A3, which we can already say is 0. Right? The area there is 0. We call this A4, A5, A6. And we can make that whole triangle A6. Now initially it just says how far in the first 4 seconds. So that's up to there. So to find the areas, well, A1, that's just a rectangle. Okay, so what do we have? This goes to -4. So we have -4 times 1. Okay, so we're just going to write 4 kilometers. Now it's negative, so I'm going to write north. Now for the first question, it's asking how far, which is a distance quantity, which is scalar. We don't need to know north, but I'm just going to write it because the second question asks for the displacement within the first 4 hours. So we'll need directions for part B. A2, well, that's a triangle, so you're going to do a half base times height, which is 1 times 4, and that's also -4. So we get -2 kilometers, or, well, -2 kilometers south, which is the same as +2 kilometers north. A3 is 0. And then A4 is a triangle again. We will have a half. Base is 1. Height is, was it 3? So that's 1 times 3. which gives us 1.5 kilometers, and that's south. All right, so for part A, you want to know the distance. All you're going to do is add the magnitudes. So you have 4 plus 2 is 6, plus 1.5 is 7.5 kilometers. For part B, if you want to know the displacement, well, we have 4 kilometers north, plus 2 north, that's 6 north, plus 1.5 south. So 6 kilometers north, and instead of writing plus 1.5 south, we can change south to north and subtract. So minus 1.5 kilometers north, okay, which gives us 4.5 kilometers north. Okay, part C says to find the total displacement. So you're going to find the areas for A5, A6, have directions. In this case, the directions will be positive south because they're both above the origin, and then add it to what we had with part B. I'm going to let you try that. If you need to see this, I will post it, or we did it in class. I don't know if things are still online or not. But part C, you'll get an answer of 1.5 kilometers south as your total displacement. All right, so I'll see you during the next lesson.